pylon to go up, move the lever into that position, pylon powers itself up, and then the computer terminal, it'll send out data that says that it's transit up, lock up. Now at this point in time, you can either go back down, go back up again. You can just play this game all you want until hell ain't but a foot away. But now if you want power, bring it all the way to the full forward position. It idles up. Then if you want to control the throttle, you have to go all the way back down to the idle position. Now it's engaged into control mode. Now you can change the speed. So at this point in time, you can slap it all the way back, and she'll stop. She'll find the park point, and as you can show to keep the control from getting hot, I don't brake this. In actual glider operations, that would be broke. In other words, it'll be solid. I'll show you what I'm talking about. Okay, it's free right now. So if I start it, she runs. Okay, then if I bring it back here and then tell it to stop, she locks and she's held into position like this. But then a few seconds later, she's free. Now in reality, it'll stay that way until it goes down. You see what I'm saying? So now let's play this game. That was great. Okay, now, so I could, theoretically, I could perpetually just keep doing this. And what it'll do, it'll just keep trying to lock. And then it has to wait for a period of time and says, okay, you're locked. I should be able to stall this thing. See this? That's that safety mode I was telling you about.
Isn't it just because it doesn't have enough power right now?
Well, no, it's actually in a very low current mode. So even if we had hundreds of amps and 80 volts there, it'll still just do this. But as soon as I get my hand out of the way, it'll run. And if you get something in there right now and stop it, it'll do the same thing, but I'm not going to put my hand in there right now. Now, when I go back, now we got the power. Now I'll just turn around and do this. This is the cool part. It'll tell you that the prop is parking. Prop is parking. It's locked. Now it's going down. It should say T down, pylon T down. And then when the pylon finds its locked position, it'll say pylon T down locked. There it is. Motors. Now these are probably the best motor money can buy for this particular application because of a lot of attributes. One of the biggest attributes is that they have very low inductance, and which means they have very little loss, and so the power that you put into them goes directly to electromotive force rather than wasting a lot of energy building magnetic flux up and down. The problem with that is that it requires much more articulation of the controller. So the more efficient you have a motor, the less the inductance and the more demand you put on the controller. And that's the emphasis we put on our controllers. And just for fun and games, here's yet another motor that we were able to run on the controller really well. Now the motor that we do have in the pylon that we've demonstrated was the JM1. Still high voltage motor, I think about a 400 volt motor, but to show you how efficient these things run, we were running these motors at around 20 volts, even though they're like a 400 volt motor. So the scale of their controllability, the power factor all the way down and up is amazing. And incidentally, the motor controller was a sensorless type, and we were just simply looking at back EMF. And we do have what we feel is a fairly unique method of looking at the back EMF in synchronous to the pulse width modulated signal. And that's what helps out a lot.